Okay, in our final video on gravitation and satellites, we're going to look at some more detail, particularly around the low altitude polar orbit satellites, and we'll also finish doing some problem solving with some previous exam questions. So let's look now at, continue looking at the weather and communication satellites now. We're going to focus more on the weather satellites, so to speak, which, and I've had to correct a mistake in the notes, are the low altitude polar orbit satellites. So just before we start on that, I don't know if you ever think about how fast you're going. It's going to become important for this first point. So I've just put this little calculation in here and I'm going to explain this. Have you ever wondered how fast you are currently moving? So we've talked about the Earth spins from west to east. So in a sense, we're all heading east. And this here is if we're at the equator, I guess, this is our radius. So this is how fast you're moving at the equator. So you're not quite moving that fast when we're closer to the Earth's axis because we're down from the equator, but it's a reasonable approximation. This is the period for 1 day. So this is basically 2 pi r on period equation. It gives it to us in meters per second, so I've just converted it to kilometers per hour. So we're all moving at about 1,670 kilometers per hour east, just because of the Earth's rotation. So you might be wondering, why am I talking about how fast you're going? Well, the first thing we need to be able to do is explain the advantages of launching low altitude equatorial orbit satellites in a west to east direction. So these are satellites that we want to orbit roughly around the equator at relatively low altitudes. Now, these satellites are usually launched in a west to east direction, so the same direction as the Earth's rotating. This is because the Earth spins west to east in a west to east direction, which we've already talked about, therefore imparting some initial velocity on the rocket before launch. So as the Earth spins, that satellite is already moving in that direction at almost 1,700 kilometers per hour, and some of that velocity is imparted. If you think about a little bit of chewy stuck to a basketball that you're spinning around, if that chewy flies off, that's going to fly off in the same direction as the ball is spinning, with some initial velocity. Now, there's actually one country in the world that launches satellites, at least, that can't launch their satellites in a west to east direction for what we might call local geographical and political reasons. So don't spend too long thinking about that, but I'll be very impressed if someone can find out the answer to that question. So if you've got a bit of an understanding of global geopolitics, you might be able to work that one out. Secondly, we need to explain why low altitude polar orbits are used in meteorology, so weather, and in surveillance. So firstly, just to explain a polar orbit satellite, so they orbit around the same axis, they orbit basically around the north-south pole. South. And so along like that yellow line there. And then what happens is, as the Earth spins around, so the Earth spins west to east around that satellite. And why I'm drawing a few little arrows is basically these satellites will orbit the Earth about 11 times per day. And as they go in their orbit, the Earth spins a little bit each time. So it spins about just over 2 hours each time. So what this one satellite is able to do is keep imaging the whole of the Earth's surface. So it keeps in the same orbit, the Earth spins around underneath it, and basically it goes past an equivalent point, not the same point, an equivalent point just over every 2 hours. So it can build up a series of photos of the Earth's surface or the weather above the Earth's surface as it does that. So, what are the advantages of these low altitude polar orbit satellites? I think these are all fairly obviously. Firstly, because they're close to the Earth's surface, they can get a greater amount of fine detail can be observed. So whether we're looking at weather patterns or surveillance, we get much greater detail from a low altitude satellite. I didn't say this here, but typically these might range from about 200 kilometres to 1,000 kilometres radius. So yeah, sort of 200 to 1,000 kilometres would be sort of typical radiuses of the low altitude satellites. Probably mostly closer to 200, I think. The other advantage is a geostationary satellite, as well as being a long way up. If you can imagine this red orbit here, it could take a reasonable picture of what's happening here near the equator, but it's not going to be able to see much detail right up here near the north or the south pole, because it basically is almost going to be over its horizon. So the geostationary satellites, or even any equatorial orbit, any satellite orbiting around the equator, isn't going to have that ability to get images of the north and south pole. Whereas with the polar orbit, because of the way the Earth spins around it, it can capture images of the whole surface. And that relates to the last advantage, which sort of explains what I've already said. The polar orbit satellites orbit Earth approximately 11 times per day and can capture the entire surface of the Earth as the Earth spins below them. So that finishes up satellites, and then just in the final part we'll look at a couple of example questions from previous exams from this sort of topic, just to give you a bit of a flavour of the sort of questions you might expect. So the final intended student learning for this subtopic was perform calculations involving orbitals, periods, radii, attitudes above the surface, and speeds of satellite, including examples involving orbits of geostationary satellites. So I've covered most of the equations and a couple of little examples in the way I've done it along the way, but I just wanted to focus here just on one previous exam question related to this. So on the 15th of February 2013, the asteroid 2012 DA14 passed closer to Earth than geostationary satellites. This was the closest an asteroid of this size had come to Earth since regular sky surveys started. The asteroid had a mass of approximately 1.3 times 10 to the 8 kilograms. So that's, yeah, you wouldn't want to get hit by that. Calculate the magnitude of the gravitational force the Earth exerted on the asteroid when it was 2.8 times 10 to the 7 metres from the centre of the Earth. The mass of the Earth is 6 times 10 to the 24 kilograms. They've rounded that off a bit. I often use the 5.977 value, but that's not really a big problem. So the information in the question, the mass of the satellite was 1.3 times 10 to the 8 kilograms. The mass of the Earth is equal to 6.0 times 10 to the 24 kilograms. When it was 2.8 times 10 to the 7 metres from the centre of the Earth, so that's a radius, equals 2.8 times 10 to the 7 metres. And it's calculate the magnitude of the gravitational force. So Fg is equal to our unknown. So what formula do we use? Fg equals G MEM, or could have done M1, M2, doesn't really matter, divided by R squared. And then we plug all the information into that. So this is only 2 marks because you don't really have to do any rearrangement of the algebra. It is just simply substitute in the numbers. And I'm going to have have to go across my line here, which I don't like doing, but that's okay. Divided by 2.8 times 10 to the 7, and we must remember to square all of that, and then we'll plug that into a calculator and get an answer. That equals 6.6, got my calculations right, times 10 to the 7 newtons. So it's just a magnitude, so I don't need to worry about the direction, although the direction is going to be asked in the next part of the question. So I think really what this is asking us is to show that we understand that the forces will be equal and act along a line joining the centre of the two objects. So we need to show that they're both acting along a line in opposite directions though, and these two lines are both the same length. So it's a fairly simple question. Much easier, I think, to get you 2 marks there than to get you 2 marks up here. Now, the next question I've picked out because I think this is a good example of an explain question that's not always done really well. So, some geostationary satellites are used for communications. A geostationary satellite cannot be in orbit directly above Australia. I sort of talked about this in the notes. Explain why a geostationary satellite cannot be in an orbit directly above Australia. So I think you'd see here a lot of students would say the orbit wouldn't be above the equator, therefore geostationary satellites must orbit the equator, or they might say it wouldn't be a possible orbit because it wouldn't coincide with the centre of the Earth. And they're not probably going to be the sort of answers, even though you probably do know what you're doing, to get us 3 marks. We're going to get 1 or 2 out of 3. So what does a 3-mark answer possibly look like for this question? So firstly, we're going to show that we understand what a geostationary satellite orbit looks like. So a geostationary satellite must remain above the same point on Earth. The orbit of a geostationary satellite above Australia would not coincide with the centre of the Earth. So we're stating what the real problem is, and this is the point I think most people would get, or get similar to that. But then how do we explain that point? How do we do the explain? Therefore it is an impossible orbit, as gravity could not provide the force causing centripetal acceleration, as gravity acts along a line joining the centre of masses. So we've really explained why. Well, we've shown we understand what a geostationary satellite is, and we've explained why it couldn't be above Australia, and we've explained that doesn't coincide with the centre of the Earth point. So we're getting to that point where we've got detail there for 3 marks. Really important, we want to get as much stuff as we know, and sometimes I think students know stuff but just don't know it or haven't practiced it enough to explain it really well. So that's why practice is important. Thanks.